All right, here is problem 19, and it is one of the classic related rates problem. You've got the ladder falling down the wall problem. And I know we did parts of this in class. We didn't do the whole problem in class, so I wanted to make sure in case you missed a part of this that we get it all done. Okay, we've got a 13-foot ladder leaning against a house when its base starts to slide away. By the time the base is 12 feet from the house, the base is moving at the rate of 5 feet per second. Part A, how fast is the top of the ladder sliding down the wall at that moment? B, what rate is the area of the triangle formed by the ladder, wall, and ground changing at that moment? C, and what rate is the angle between the ladder and the ground changing at that moment? Okay, lots of things to label in this picture. First of all, they told us the ladder is a 13-foot ladder. We can label that right away. It is okay. We don't need to give that a variable because it doesn't change this problem. 13-foot ladder is always 13 feet. Okay, going horizontally, and again, this black line here, over here, this is our house over here. And so we've got, going vertically, we'll let that be our y coordinate. Horizontally, we'll call that our x coordinate. And we label those as variables because this ladder truly is going up and down, and it's going to the right, so x and y are changing. Those need to be variables. All right, we read up here the second line. By the time the base is 12 feet from the house, the base is down here, so that's when x equals 12. The base is moving at a rate. A rate is a derivative, and it's the base. So the derivative of x with respect to time is 5. And again, the space is moving away from the house. X is getting larger, so dx dt is a positive 5. How fast is the top of the ladder sliding down? So our question for part A becomes, find dy dt. What does dy dt equal? And once we get this part done, we'll kind of consider part B and part C. How fast is the ladder sliding down the wall at that moment? All right, so we've got dx dt. We're looking for dy dt. We need an equation that relates dx dt, that relates x and y. And again, it's a triangle. Our most obvious choice is, how about the Pythagorean theorem? So we've got x squared plus y squared equals the hypotenuse squared. But guys, remember hypotenuse is the length of the ladder. That's a constant. I can sub that in right away. I do not sub in 12 for x, because that varies as the problem goes on. So I don't sub in anything else that varies until I've taken the derivative. Let's take the derivative. And again, it's a rate, so we'll take the derivative with respect to time. We'll do that to both sides. The derivative with respect to time. Left side I get 2x, left side, 2x, dx dt, plus 2y, dy dt. And the right side, I've got a 13 squared. That's a constant. The derivative of constant is 0. So now I'm almost there. I'll sub in. I've got 2. X is 12. Dx dt was a positive 5. This looks good. I've got a 2. Oh, shoot. What is y? We come back here. We had x is 12. The ladder is 13. We know the Pythagorean theorem. 12 squared plus y squared equals 13 squared, so we've got a 144, and a y squared is a 169. So you can solve that and figure out y equals 5. So we'll sub in the 5 for y. We're kind of seeing a symmetry here. So y is 5, and dy dt was our question. This whole thing equals 0. If you want, you can immediately cross out the 2's and the 5's, or we can just multiply it out. And so this is 24. 24 times 5 is 120. So on the left side, I've got 10 dy dt. I'll take the 120 to the right side. I get negative 120. And I've got part A completed. Dy dt, divide by 10, and I get a negative 12. And it's y, so I know my units are feet. And I believe it was feet per second. Hopefully you're not surprised by the fact that y was negative, because look, it's sliding down the wall. Your y distance is getting smaller. Because your y distance is getting smaller, your dy dt is a negative. Okay, that completes part A. Let's see if we can move on and get part B. Part B, let's read it, and then we'll be ready for it. At what rate is the area of the triangle? So you come back here. I won't color this in too much because we got a part C. but the area of the triangle. We see the triangle. At what rate is the area of the triangle formed by the ladder, the wall, and the ground changing at that moment? Okay, area of the triangle. So now we're ready for part B. Let's give ourselves just a little bit more space. So part B, area of the triangle. And I know the area of a triangle. The area of the triangle is 1/2 the base, which is x, and the height, which is y. And one thing just to think about as that's going down, is that area getting bigger or smaller? At certain points, the area would be getting bigger when the ladder was very vertical. So if you have it way up and down here, as you come down, the area gets bigger. Then there'll be a certain point you reach where the area gets smaller again. So at this point, when x is 12, is the area getting larger or smaller? We will find out. Let's take the derivative with respect to time. Oops, make that somewhat neater. The derivative with respect to time, I'm taking that at both sides. The left side I've got the ADT. And the right side I note. First of all, 1/2 is a constant, connected with multiplication. That factors through when I take the derivative. I'll just put a big parenthesis here. X and Y are both variables. I need the product rule. 1, D2, and 2, D1. And as you're doing this, you're kind of grateful again for part A because we're going to need that dy dt, aren't we? So I'll sub in. I've got 1/2. I've got my big parenthesis. We said x was 12. dy dt, we just figured it out. That was a -12. The signs are very important. We knew y, the y coordinate was 5. We figured it out in part A. Dx dt was also 5. And so I've got 1/2. So dA dt equals 1/2. And it looks like a -144 and a +25. So it looks like a -119/2, which would be just a little less than 60, right? A -59.5, and it's an area, so I know that would be square feet per second. So at this point in time, the area is getting smaller. And maybe your intuition told you that, maybe not, but analytically, very clearly, that is our answer. Okay, let's get part C. Part C. At what rate is the angle, and the angle theta, between the ladder and the ground? So we need an angle theta between the ladder and the ground. Here's the ground, here's our ladder, here's our angle theta. And here's where I vary a little bit from the solutions manual. I'll do it one way, and if it doesn't make very good sense, you can always come back, look at the solution manual. They have another way. So what rate is the angle between the ladder and the ground changing at that moment? Angles make me think of trig functions. And we'll come down here, we'll resketch the triangle a little bit, just so we got it here. And so I've got part C. And just a rough sketch again, we've got our triangle. We're looking for theta. We knew x was 12. We knew dx dt was 5. We knew y was 5. And we figured out dy dt was a -12. Here was our x, here was our y, and a 13 is okay to label because that doesn't change in the problem. Okay, so we need a trig function, and you're thinking sine, or cosine, or tangent. And any of these will work, but since the 13 is a constant, it might be nice to include that. And since they gave us the initial information about x and dx dt, it might be nice to use that. So I've got those two sides. I would lean towards using cosine, understanding that any of the three would work. But sometimes a choice like this will make a little bit of the work easier. So let's go with the cosine. I know the cosine, SOHCAHTOA. The cosine of an angle is adjacent over hypotenuse. I don't sub in for x because, again, that changes throughout the problem. I can sub in the 13 because that does not change. Okay, here's where I vary from the solution manual. I would take the derivative right away. Let's take the derivative with respect to time. And again, you can kind of argue this either way. I like my way, and I'm sure the solution manual author likes their way. Let's take the derivative with respect to time. The derivative of the cosine is negative sine of theta. And again, don't forget the chain rule. The inside derivative is d theta dt, the chain rule. So derivative of theta is d theta dt. On the right side, that 1/13 is a constant connected with multiplication. And the derivative of x is dx dt. Okay, guys, we're almost there. I know what dx dt is. I don't know, however, what the sine of theta is. So I come back, I look at my triangle, and I notice here in my triangle, now that I've taken the derivative, I know, look, x was 12. I knew y was 5. I know SOHCAHTOA. So the sine of theta is the opposite 5 over the hypotenuse 13 at that moment in time. So I can use that value as I sub in. So I've got a negative. The sine of theta is 5/13. d theta dt is what I happen to be looking for. Here I've got a 1/13, and dx dt is also 5. So I note the left side, the right side are the same thing. I'll divide, and I'll get d theta dt equals a -1. What are my units on an angle? Well, anytime you're using calculus, and here I took the derivative of cosine to get sine. So calculus on a trig function, it's our assumption that we're using radians because the derivative of cosine is sine. That's only true if we're in radians. If you're in degrees, you get another constant in there. So our units here are radians. I believe this was per second. So the angle is getting smaller, and again, if you think about that as the ladder slides down, sure enough, the angle is getting smaller. d theta dt is -1 radian per second.